Newton's second law and the momentum. So a system would have a change of momentum only if there is an external resultant force acting on the system. Actually, the net force causes the change of momentum of a body. For example, if we are a ball here, we must provide a force so that its velocity will change. That's why the net force is not just cause the change of the velocity, but also the momentum. So let's relate the momentum and the force together. By F net equal to ma, the A is V minus U over T. So we can substitute into it. We will find that m times V minus U over T, which is the mv minus mu over T. And the mv minus mu is exactly the change of momentum of an object. If we back into the history, actually the force is derived by the rate of change of momentum. So here we usually learn the force first before we learn momentum, but in fact we have momentum first in history and then we come to the force. What is the T here means? The T here means the duration. We'll talk about it a minute later. So the net force acting on a system is equal to the rate of change of momentum of a system. So if the change of momentum that causes a collision, then the net force causing the change of momentum, we call it the average impact force. Or we can write in another way, which is the average force of impact. So please note that when we use mv minus mu over t, we are finding the net force. Let's consider this. If we have a person that's playing the tennis ball, for example, if the ball with velocity u flying to the person, and then she hit it back with a force, and the time t is the duration of the ball touching the racket. This is the time t, and the ball fly back with the velocity v afterward. So we will have the change of momentum and also the time. If we consider a ball throwing to the wall and then is rebounds by the wall, so the wall will provide a force to it in the time here. So
watch how the tennis ball is deformed on hitting a wall.
Do you see when
Let's
the ball
watch it again from the
on the
side.
wall,
what caused the
there
ball
is a
to
time
deform?
for the ball to deform and then restore to its original shape? This duration, the contact time, is the t we mentioned here. So make sure you note that what is the t means when we use this equation. The t is the duration of the object hitting or touching the wall or something, so that it will bounce back later on. So you can see this is the meaning of the time here. And then it's moved back with the final velocity, so we will have another momentum in this case. Let's see how do we use it. For example, if we are playing a game with small disc on the table and the rod is hitting on it with a force, and if we know the duration time of the contact, we can find the net force and the change of momentum with the following relationship. So we can use this and substitute all the value and make sure the time, the ms millisecond, means 1 over 1000 seconds. Then we can find the speed of the disc after it's liftward. Then what's the work done on the disc by the player? The work done is actually the KE gain. So if we know the final speed of it, we can use it to find the work done, that work on the disc. Let's see another examples here. Suppose if we have a ball of certain mass, release, and rebounds to a different height. Then, what is the speed just before it's hitting the ground, and the speed is just after hitting the ground? Now we can observe that there should be difference. Because the ball cannot rebound to the same height, the bounce back height is smaller than the original. So let's consider the downward flight first. By using the energy, the potential energy loss is equal to the KE gain. So that we can use this expression to find out the velocity, the V1. Actually, with this method, we can also neglect the mass of it. We can directly find the V1 here. So we know the speed of the ball before it's touched on the ground. By using the similar method, we can also find the upward flight and use this upward flight to find the velocity V2 in this example. Okay, so this method, I think all of you should be very familiar with because we use it for many times in the previous chapter about energy. Okay, so we got this two velocity. How can we use it? We will use it in part B. In part B, we know the time of contact for the ball with the ground is 0.5 seconds. So what is the average net force here? As we know, the F net is equal to mv minus mu over t. And because this is a vector equation, so we have to take the direction with positive. So if we take upward as positive, then when we substitute the value, the downward V1 should be in negative value. By this, we can find the F net here. Then part C, find the normal reaction force acting on it. Do you have a question in mind? Normal reaction, isn't it just equal to 7.13? Surely not, because the F net is 7.13. The value in part B is just the F net, but here we are looking for the R. We know that the ball can go back, so the R should be larger than W, so that we can have an upward net force. So in this way, we can find the normal reaction acting on the ball here.